Okay, cool. So you guys are working on the adders. That's the homework due on Wednesday. So what was the question that you had, Shauna?
Okay, yeah, so it's actually like number 1A. I just I don't know if I'm overcomplicating it. Um so I get like for Cariadder, I'm working under the assumption that the sum is A XOR B XOR Cn, and then C out is A and B or A and Cn or B and Cn, right? So here's my question. Like the propagation delay, the longest path, I know goes through the C out. And that's just, I think, the full adder delay times the number of full adders we have.
Pretty much, yeah.
Okay, but my problem is with the contamination delay. So I was assuming the shortest path would be just through the sum. So A XOR B XOR Cn, but I got confused because the instructions say assume that each two input gate delay is 50 to 150 picoseconds. And I thought that's a three input gate delay for the sum. So I didn't know like if I should just use 50.
So it depends on how you implement the full adder. So in this case, I would just treat it like if you're at all entering a full adder and then exiting a full adder, so the path from the input to the output, which in this case would be either A or B or C in to sum, just treat
Okay.
that as a full adder delay because you're going through the full adder.
Okay, so that would just be yeah, A. Okay, so hold on, let me see. The contamination delay for the following types of 64-bit adders. So if we had a 64, so that would be 64 one-bit adders because a full adder is a one bit.
Yeah.
And then so it would just be like 64 times 50 for the contamination delay.
Well, the contamination delay would just be 50, or sorry, 150, because the very first signal that basically asserts is some bit 1 or some bit 0, the output of the very first adder. And that's ready after just one full adder delay. So, so since that's the fastest signal, we'd take that one. Now, if you were asked per signal, then it would be either 150 for some bit 0 or 300 for some bit 1 or 450 for some bit 2 and so on. But it seems to me that she's asking it in terms of the overall system. So I'd say just 150 picoseconds because that's the fastest you can get out to some bit 0.
Okay, so it's not, I was thinking it would be 64 times and also wait, like I guess I'm like just really confused. Why are we given the two input gate delay if we have the full adder delay
You're going to need that for the ripple carry adder. Or sorry, for
for
the
the
carry look ahead adder. Because the carry
yes,
look ahead adder has both
the
the,
two gate.
yeah, it has a bunch of two
Oh,
gates. So if you were to look like in your
right.
slides, you'd see the long chain of and ors iterated,
Yeah.
and that's what you're going to use it for.
Oh, okay. And yeah, that's the last one. Or it's yeah, the two gate times however many adders we have. Okay. Yeah, I think I was way overcomplicating this because I wasn't really confused on the carry look ahead. I was like more confused on the ripple carry. But so it's wait, but I'm still confused. Why would it just be 150 if we have 64 adders?
So remember that the contamination delay is the quickest path through your circuit. And so if you're looking
Yes.
for the fastest way to get through your circuit, it's not to chain all the way down through the full adders, it's to exit at the earliest spot. And the earliest spot is the least significant bit position. So like when you're doing regular addition and I said do 179 plus 253. Well, you'd start with the 9 in the ones place plus the 3 in the ones place. That's the very first thing that finishes. But it
Yes.
is one of your outputs. So that would be the contamination delay. Same deal
I told.
here, some bit zero.
Yeah. Okay. That totally makes sense. Okay. Cool. And then the propagation delay for that, though, would be the 64 times the 450.
That's right,
Um,
yes.
okay. Okay. I think I understand now. I was like, I've been like struggling on that part A for an hour and I like rewatched all the videos and I knew it was something stupid that I was just missing. So,
No, you're good. It can be very easy to get confused with these kinds of questions. It's very easy to make yourself think it's more complicated than it is.
yes. Yes, that is overcomplicating things. Okay, that was my main question that I was stuck on. So I'm going to mute myself now.
Okay, cool. Did you have any questions for me, Good Noodle?
Um, yes. I remember we talked about timers, and I was wondering, like, I understand that I would probably be using a variable for that, but then where would I place that exactly?
So you're referencing like a 1 hertz timer or something like a.
I remember you said that like I could either make multiple modules of a clock, and then just use that for my game, or I could use a timer. And I was wondering like what you meant or what you meant by that.
Um, I don't recall exactly what I said, but to expand on that, you can make multiple different timers or multiple different clocks for your system, all derived from the same 50 megahertz clock. So you could just take your 50 megahertz clock and run it into maybe 3 separate modules. One module which produces like a 1 hertz clock, one module that produces like a 25 hertz clock, and then another module that does like a 600 hertz clock or something like that. That's one way to do it. You could do exactly the same thing, still 3 different modules, but you could make it one parameterizable module that you can instantiate with, well, different parameters so that you can get a 1 hertz versus a 50 hertz versus a 200 hertz clock, all using the same module. So I think what I meant, I may be incorrect, but I think what I meant when I said that is you can either make 3 separate modules to do all 3 different timers or 3 different clocks, or you can make one parameterizable module to implement all of them. So it just depends on how you want to do it.
Okay, that makes a lot more sense. Yeah.
Any other questions?
Aside from that, I'm good. Thank you.
All right, cool.
So can I make sure I'm understanding number 2 right too?
Yeah, sure.
Since there's no other questions. Okay, so for number 2, I'm just doing our regular like T hold and T setup equations using the information given. I guess I don't understand why I'm given the figure or like what I need the figure for.
The figure is just to basically, I mean, it's just a visual because you could be asked these questions without the figure and it'd be the same question. So it's just showing you exactly what circuit you're looking at. You're looking at a register which contains the inputs A, B, and C in, and that register is going to spit those inputs to the full adder, and then the full adder is going to do some stuff, and then the outputs of the full adder, which are C out and the sum, are going to go to the second register, the, I guess, receiving register. And so it's just it's just a schematic of what it is that you're actually checking with your hold time constraints.
Oh,
Just to be specific, I guess, but it's the same process as you've been doing.
okay. Yeah, no, that it's helpful to like see what's going on. I just didn't know if like that changed the problems or the equations. And
No, it's the same thing.
okay, so we just do the regular equations using what we found in exercise 1.
Yep.
Cool. And then number 3, we like went through an example of this with it was like a 4-bit block or whatever. So I think I'm pretty okay with that.
You can also look at the slides. I think it's like
Yes.
page, let's see, I think it's like 100 or something.
Yeah, that's the one we did in class. It was what was it? Yeah, 8 4 bits or something. Yeah, 8 blocks, 4 bits. Um, okay, good. So I think I understand what I need for tonight. So perfecto.
Cool.
Okay. Good Noodle, do you have another question?
I was looking at number 2, and I was just wondering, is it safe to assume there's no like that timing hazard with the different clocks? I can't remember. I can't remember what it's called.
Oh, these are the same clock. You don't have to worry about
Oh,
that.
same clock.
I think you're
Oh,
thinking
okay.
about metastability, I believe.
Uh,
Or
yes, but I remember in the aside in like the first part when we were learning about delays and frequencies that there was like either it was one clock was faster or one clock was slower because of how
oh,
it was
skew.
receiving.
Yeah.
Oh, skew. There you go. Yeah. So it's
Yeah.
the same.
Assume no
Oh,
skew.
skew.
Unless
Okay, thank you.
it says there's skew, because I mean you could be asked, but you're not even given a number here. So the only way that it could be asked of you to account for skew is if they specifically said, how much skew can the circuit tolerate? But that's not asked in this question, so you don't have to worry about it. Just disregard any skew.
Thank you.
Okay, I have like an off-topic question, but I was trying to like pick some classes for next semester, and I just want to know. Actually, Dr. Harris said like I could, ask you what your opinions were on this stuff. Like, okay, I think my first question, what is an embedded system? Like what are you doing with that? Are you using RISC-V, and are you using like the FPGA board? Like I guess I don't even know what that means. So,
Yeah, I wish I was at home. I'm not at home right now. I have on my desk. I have an embedded system, the one that we used for 301. But basically, you can think of an embedded system as like a little mini processor. So whatever's sitting inside of your laptop is a relatively powerful processor, or on a desktop if you have one at home. Whereas embedded systems are like tiny little things, like the actual chips, the actual processor chips are around that small, not particularly large. And then for the class, you'll be using that processor that's on a board, which has a bunch of pins that you can plug into and stuff. And so basically, embedded systems is about learning how to, well, use assembly, not RISC-V in particular. It depends on what processor you're using, but an assembly language like RISC-V or a higher level C code to program one of those embedded devices to do basic input-output functionality. So, for example, you can very, very simply turn on an LED by typing up some code that the embedded processor can run. And so on the board, you'd have an LED, and you type up some code that's like, okay, I want this pin to go to a 0, and then that turns on the LED. Down to complex things like having code that can read in the output of a, what's it called? An IMU, which is essentially an accelerometer and a gyroscope and a magnetometer, which are basically measurements to figure out rotations and how far you're traveling in directions and things like that. And so you can have a system which reads in information from this IMU, which is, I'm trying to remember what IMU stands for. I think it's like inertial momentum unit, something like that. But anyways, you can read in stuff from that using a specific protocol. I believe it's, for the one you guys are going to do with, I think it's the SPI. I might be wrong on that. But you'll learn about different protocols and how information is communicated between devices. So you're going to learn a little bit about the protocol that you'll use to basically request information from the IMU. And then for the IMU to send it back to you, you'll read it in. And then using that data, you can calculate things. Like, for example, we did an assignment where we would read the rotation of the IMU, and then we would basically use that exact amount of rotation to then turn a motor, basically to counteract the rotation. And the idea is like, if you have a drone and it's has a camera on the bottom, if it's leaning to one side, you don't want the camera to also lean with it. You want it to be straight, and so the correction basically makes it lean straight, even though it's leaning to the left. So you read in your IMU data, and then you can basically correct the orientation of the camera, and so you can see at a flat angle still. That's like an example of what you might be doing. That's like a project example kind of thing. And so you'll work your way through it. Your first few assignments are going to be like your first, I think, 1, maybe 2 assignments are going to be done in assembly. And it's not going to be RISC-V. It's going to be whatever assembly it is that corresponds to that particular processor. For us, it was, I think it was just called AVR assembly. It's not particularly difficult to get used to assembly once you learn one of them. Just like coding languages, it's a lot easier to learn how to move from one language to another than learning from scratch like the first time. So since you guys have a little bit of an introduction to assembly, it's not going to be too bad when you learn a new one. So you learn to program in that, but only for the first 2 assignments. After that, it's going to be all C code, and you'll learn how to do, basically mess with the embedded system and have it do stuff with the GPIO pins. You'll learn about PWMs, which are basically, you can create your own square waves with their own frequency and duty cycles. You can use those to control things like, for example, a motor. And yeah, that's most of what you'd be doing.
Okay, that's really helpful. Because I had literally no idea what it even was before.
Yes. It's mostly a coding class for the most part. But you do need to know a little bit of hardware background to kind of get the ideas.
I like the software side, or the coding side, so I'm excited.
Okay, good. You got any questions for me, Good Noodle?
No, I was just thinking more about what you said about embedded systems. Yeah. You don't get to use Rust.
It's a fun class. You get to do a bunch of pretty cool stuff. You kind of get out of it what you put into it. A lot of people who didn't really like it that much, some of my peers, it was mainly just because they, didn't really want to put in the time and effort into the class. And if you do put a little bit more effort into it, it's quite a fun time. It's pretty cool learning about the different stuff you can do. And there is a pretty decent market for embedded programmers, because embedded systems are used everywhere. Literally everywhere you have a piece of electronics, it is going to have an embedded system in it, whether that be to control things or just to have a processor. It's in basically any electronic you have.
A Raspberry Pi is an embedded system, right?
Yeah, you can think of it as an embedded system. It's what's it called? You can basically use it as one, yeah. Because the little boards you're going to get, they aren't going to be Raspberry Pis, they're not going to be Arduinos, but they're basically like them. You can use them very similarly in terms of like inputs and outputs and stuff. Just the way you code on them and interact with them is different. So like Arduinos use the Arduino IDE versus your embedded system that you guys are going to have in 301 is going to use, the AVR assembly and C code as the software that you use to communicate. So in terms of functionality, yeah, it is.
Is there any benefit to learning MATLAB? Or is that like more?
Well, I don't know MATLAB. I've never done anything in MATLAB just because my classes haven't required it. I imagine that it would be helpful, but I'm not too sure what in particular you would really want to use it for. I know a few of my classmates who have used it for one of their research projects. where they did some MATLAB stuff for a software-defined radio. I don't know too much about the details, but from what I've heard, it is a pretty useful software to know. Or a useful language to know.
So I don't mean to put Good Noodle on the spot, but I have a quick question. Were you, Good Noodle, able to import your pin assignments, or did you have to do it manually on your project?
Like projects in general, or
Project, yeah. Or I don't know if like you've done that yet.
yeah. I just used a QSL file.
Oh, I don't understand what is going on. Like, not only for that last assignment, I had to do it manually, but for my final project, I've had to do it manually. I still get those same errors, which makes me think I must be doing something wrong. Be-
I mean, you could try and run through one of your labs again and see if the same issue pops up.
I think the problem is I did all the labs on the lab computer, and like these are the first time I'm trying to do the board on my home computer. So I'm like, there's must be something weird. I'm gonna try to do it on the lab computer and see if it works, and then I'll know.
Okay.
I don't know why I'm the person having this issue, but it's like doing it manually just kills me. It's
You might be able to ask your lab TA to see if they know anything about what might be different between the lab installs versus the one you have on your computer. I think the ones in the lab use version 13.1. Is that the one that you have installed?
I'm on my different computer. I thought I was using the one that was in like mentioned in the lab, but it could be a different one. I want
There's 14.1, which is pretty easily like found online, and 13.1 is not. And 13.1 is the one I believe that the lab uses. So
okay. No, I think I'm on 14.1.
okay.
So that might.
I don't know that that's necessarily the issue. I've never had trouble myself trying to run 14.1. It's been fine. I've never had that issue. So I don't know. Maybe you could just ask your lab TA and see if they know anything about why it would be acting strange.
Yeah, I think I'm just gonna have to go in with my laptop and the board and like sit with him and be like, what am I doing? Because yeah, the manual stuff it's like every time I do a new project, I have to manually do it, and
It's not fun, yeah.
no, it's terrible. So, okay.
How are your guys' projects coming along?
I got my input working, so now I just gotta set up the logic for that. But
Okay, cool. Nice.
yeah.
I got my like random number to output on the board, and then my slide switch like binary input. I like set it up to do like output 1 if I got it correct on the LED and 0 if not, and so that's working. I think next is just setting up an FSM to like get the same like lock in the answer using the same like button that I'm generating the random number for, and then putting a scoring system. But
Okay, cool.
I like have something output on the board, which I think is my main concern of like not getting anything to work. So
Yeah.
I have like the basis of the game is there. It's now just like adding additional stuff.
That's exactly how you want to do it. Slow and steady, small stuff, get something working. Good.
Yeah, that was the best advice was like, because remember, like we came in and we had all these like nothing worked.
Yeah.
And I ended up like deleting everything and just rewriting like one module and like making sure it output.
Yep. That's the way to do it.
Yeah, and that's the only way to do it. So
Yeah.
that was nice. Thank you.
You're welcome. Trust me, I learned that the hard way.
Yeah, like I don't know why we were worried about like doing all this fancy stuff before we could even output a number on the board. It was
Yep.
definitely like trying to run before you can walk. So yeah, it's going okay.
Good.
I just don't know how much time. Like I wish there was more time to do
Yeah.
this. That's kind of like the hardest issue is the time management. So
It is. It is. So, besides the homework that's due tonight, you guys have two other ones, 21 and 22. And then I believe it's just your midterm, yeah?
yeah, it's just two more. The one that we were going through on this call, and then one on like next Monday or something.
Okay. And it looks like homework 22 actually is a pretty short one, or relatively short one.
Yeah, what is the like what should be the game plan for the final? Just I feel like my only game plan right now is like to review all of the homeworks and like redo a problem from like each kind of section and then the mid. But I don't know, it just feels like a lot and I'm not good at like prioritizing or managing my time.
No, I
so.
think that's a pretty reasonable way to do it. You could probably, you guys could maybe ask Dr. Harris to see if she gives you a practice exam, but, or a practice final. Though I will say that most of the time she doesn't do problems exactly like on the final. She might do a few, but she'll change up the wording, change up the numbers, and then add in a few extra ones and take off some of the ones that were in the practice. It's more just to get an idea of the flavor of how she asks. But to be fair, you guys probably have an idea of that from your first two midterms.
Yeah, for sure.
Yeah, I guess what we can do is whenever you guys have time, just look over the homeworks and maybe like write down a list of problems that you're not too sure about, that you're not like 100% on, and I'm more than happy to go over them in office hours until, well, for as long as we need to.
Can I ask you, what core classes did you take that you really liked?
Well, right now I'm taking EE 421 with Dr. Baker. That's for the digital design core. And it's pretty much about how I'm sure I've talked about this before during office hours, but it's about how integrated circuits are made. So you learn about how to do layouts, basically how to design the stuff within those black plastic packages, how all the stuff works in there, and it's a pretty fun one. We're finishing up our course project right now, which was to make a buck converter, which is a step-down voltage converter. And it was definitely like we learned a lot. I'll put it that way. We learned a hell of a lot of stuff in that class, and I thought it was really interesting. I had an excellent time taking it. Let's see. I took CPE 404, which is also part of the digital design core. And in that class, you guys haven't taken CPE 300 yet, but you're going to talk a very little bit about processor architecture at the end of this class, at the end of 200, maybe for like half a class or something. If that, you might not go over it. But, learning about processor design, and in CPE 300, you learn about more details about how to implement a processor. Specifically, if you take Dr. Regentova, she teaches you guys about how to implement a MIPS processor, and MIPS is very similar to RISC in terms of the assembly language. They're almost identical, just a few minor differences. So you learn how to implement the processor hardware, how to run code on it, and then at the end of the course, you'll be able to design your own little microprocessor for a different instruction set architecture. That's kind of your like final project. And then in the core class CPE 404, that's basically processor architecture part 2. You learn about extra things to add onto your processor to make it better. So things like branch prediction for making sure that you waste as little time as possible reading in the incorrect instructions when you have a branch. And we did a project about implementing a branch predictor, so that was a pretty fun project. Let's see. You guys... Well, it depends on your other cores. So for me, I happened to take another core, which was CPE 405, and that one, I'm not using it as a core. I used it as a professional, but that's one of the core for, I think for computer networks, CN. And for that one, it's mostly theory, where you basically learn about the most efficient ways to encode data into binary. And you don't really do like implementation of hardware. It's, like I mentioned, it's really just theory, but I thought the theory was pretty interesting, so I had a fun time in that class. And then right now I'm taking 2 other core classes, CPE 403 and 476, which are Advanced Embedded Systems and Robotics, respectively. Advanced Embedded Systems is just Embedded Systems Part 2, and Robotics is a class where you get to, as you've seen when I bring in the stuff sometimes for office hours, you basically build up a robot and you learn how to make it do stuff. so both pretty interesting, definitely good classes. I'm not too sure about the other cores. I haven't taken any like IoT classes. I decided not to do any of those. But I've heard that they're pretty interesting too. So not a whole lot you can go wrong with. More so just kind of go for the stuff that sounds most interesting to you. And it'll probably work out.
Yeah, that robotics one is definitely on my list. Sounds super awesome.
Yeah. Okay, cool. AJ, you just came in. Did you have any questions for me? Oh, that's right. I always forget. You don't have your mic. I need to check the chat. Let's see. No, you're fine. We started a bit late, so I'm probably going to end at like 6:50, because that's when I started at about 5:50. I assume you mean the one that's due tonight. Is that right? Okay. Yeah, let me open it up. That's homework 20. Counter problem. Counter turn 10 megahertz, 300 hertz, 3 digits of precision. Okay, yeah, we can do that. So I will go ahead and share my screen, or part of it at least. Okay, so let's do this one. Desmos. Properties. Okay. There we go. And I'll do this. So I'm going to have this open mainly just for calculations. And what I'll do is I'll try and verbally explain the idea of a counter and kind of type up the equations for him. If you want me to draw out the schematics too, I can, but the counter schematic is the same one that you used for all your other homeworks and examples. So it's the exact same thing. You're just changing like the sizes of the bit widths of the register and like the multiplier that you're using on the input. Let's see. Let's do that. Okay, cool. I'll just leave it like this. So that's not what I'm doing. There we go. Okay, so when you have your counter, remember that you can change basically two things. You can change the bit width, and you can change the multiplier. Those are the two big things you can change. So in order to get more precision, you need a higher bit width. You need more bits for your register. So as an example, I'll say that I'm going to have a bit width n of 32. That's what I'm going to do. And what I want to do is I want to convert the frequency of my clock, which is currently 10 megahertz. So I'll write it as 10 times 10 to the 6th. That's 10 megahertz. That's my current clock frequency. And I want to convert that into basically a desired clock frequency, which is going to be my, I believe I said 300. Yeah, 300. So I want 300 hertz. That's my goal. And so what I'm going to do is I'm going to say, okay, here's going to be my frequency that I get. I'm going to call it my actual frequency because I'm not going to get exactly 300. So you take your frequency of the clock you have and you divide it by 2 to the power n, where n is the basically the number of bits you're using. That's your bit width. So that's how many bits your register is going to be. And then you have an m value where m is your multiplier. And that's essentially the number that's going into the adder. So remember, for a counter, you have a register, and then you have an adder feeding it into the input of that register. And the other input of the adder is a number, like 1, 2, 17, it doesn't matter what it is. So here, m is that number. So if, for example, I did 86, you'll notice that for an input frequency of 10 megahertz and a multiplier of 86, when you plug these numbers in, it looks like I get a frequency of about 0.2 hertz. Okay, well, let's maybe step it up. Let's do 860. Okay, that's about 2 hertz. I want it to be 300 hertz. So maybe I'll do, I don't know, let's do 129. So that right there is about 300 hertz. And so you'll notice that just by plugging in different m values here, depending on what my bit width is, I can get pretty close to the frequency that I want, 300. Now, it's up to you as the designer to figure out what your bit width is going to be. The more bits you have, the more precise your clock is going to be, but also the more hardware you're using to create your counter. You don't have to. I'm brute forcing it just to show it as an example, but you don't have to. There's ways to analytically, basically figure out the best answer. It's just it'll probably be faster to brute force it. So up to you. I would say the best way to start, or the easiest way to start, is to start with an M of 1 and figure out what the smallest n you can go is, so the smallest bit width. So 15, 14. 15 is the smallest I can go because m equals 1 is the smallest it goes. And then if n is 14 or lower, you can't get a low enough frequency. It's 610. At n equals 15, that's almost 300. So that's the lowest we can go. So your bit width is going to have to be at least 15 bits for this one. I would say, you can try 16, but it's not going to be very precise because then n is going to be equal to 2 and you have the same thing. So, maybe try 20 and see what you can get with that. You'll probably have to pump up m to like 30 is my guess. 31, 32. Yeah, about 31, 32, and that's getting closer, a little bit more precise. And so you can just keep pumping n up until you get precise enough. So I think for this homework, they want it at 3 decimal points. Oh yeah, so they just want it to be at least 300 because it's 3 significant digits of precision. So as long as you got 300 here, you should be solid. And I think, yeah, and I think that's pretty much it. So any other questions on that, AJ? Yeah, you can just estimate them. You want to get, like I mentioned, at least 3 decimal points of precision, but it doesn't have to be exact, because again, it's within a range of 3. You could, if you wanted to, be ridiculous and say, I'm going to have a 100-bit register, and I'm going to do my M as that's too many bits. I'm going to tone it down. It's a bit ridiculous. I'll do 40. And, you could tune your M value up to whatever you want. Let's do 5, 7, and there you go. That's a solution. Not a particularly optimal one because the precision isn't exact and you're using a lot more bits than you need to, but that's one way to do it, yeah. Just don't be excessive. I'd say, 40 bits is a little bit much. I'd probably say don't go above 32 bits. I don't think that many bits is necessary. But yeah, don't worry too much about being the most optimal configuration. Just try and get something to work below 32 bits and you're good. Yeah, you're welcome. Any other questions before we end our office hours tonight?
Not for me. Thank you so much.
You're welcome. You're very welcome.
Thank you very much.
You're welcome. All right. You guys all have a good rest of your night. And same time tomorrow, 5:30. I should be in the Great Hall tomorrow, so you don't have to worry about that. But yeah, you guys all have a good rest of your night.
You too. Good night.
Thank
See
you.
ya.
You too.